Okay, the last thing I want to consider in this block of material are just some additional alternatives for doing further analysis with variables that don't necessarily meet the standard criteria. Let's see what we mean by that. One option is utilizing what are called dummy variables, and these are placeholders that are used when we have categoric and non-numeric variables. As you might imagine from our analysis, it does rely on the variables being numeric. But what happens when we want to consider the potential impact of a variable that is categoric? And let's see how we can deal with this idea of dummy variables can help us out. So let's take a look at our data set once again. And we have our information on our houses. Supposing we wanted to see if we can do an even better job of modeling the selling price of these homes. And we've looked at value, square footage, number of bedrooms, which turned out not to be significant. But we can well imagine a number of other things that might be significant. Some are numeric, like, for example, the distance from the nearest Walmart, or things of that nature. The size of the lot, for example, would be another potential numeric variable that could be significant. But there also are variables that might be very important that are categoric variables, such as, is this particular property on the waterfront? Is this particular property zoned for an A-grade school? Yes or no? And particularly when we have these bi-level categoric variables where we could say yes or no as an answer to the question, there's a very powerful way that we can model this variable. If we were to code that yes or no with a 1 or a 0, where 1 implies yes, the criteria is met, and 0 implies no, the criteria is not met, then we can actually take those numeric values of 1 and 0 and use those as values in a numeric variable. Treat them as numeric. Only in the case where we have just those bi-level 1 or 0, we can treat them as numeric and actually have a meaningful output from the analysis. So let's say we were interested in whether or not this property was on the waterfront. We could create a new variable called waterfront and just populate it for the respective houses, depending on whether or not they fell on the waterfront. And we can keep on going, obviously. I'm making up data here, but we could capture that information for the actual houses. And then we could run the regression, including that new variable called waterfront. And if it did turn out to have a slope that was coefficient, a slope or coefficient that was significant, how would we interpret that? Well, what we would say is that, again, like all slopes, it's the amount that price would increase, right, that our dependent variable would increase for a unit increase in our independent variable. And our independent variable is waterfront. So what does a unit increase mean? It means we've gone from not being on the waterfront to being on the waterfront with all other things remaining equal. So if this ended up to be a significant coefficient for our variable waterfront, then that coefficient, that amount, that dollar value that makes up that slope, or that coefficient, would be essentially the premium for a house being on the waterfront versus an equal house being not on the waterfront. So it becomes a very useful way for us to look at categoric variables, again, particularly bi-level variables. If we had multi-level categoric variables, for example, what was the grading of the nearest elementary school, and the options could be A, B, C, or D. What we would need to do in that case is we'd need to create a separate bi-level variable for each of those grades. So is the nearest elementary school an A grade school, yes or no, 1 or 0? Is it a B grade school, yes or no, etc. We'd create those for every one of the possible options, A, B, C, or D, let's say. And then what we'd have to be very careful to do is when we were to include those as potential explanatory variables, it's very important that we do not include all of them in the analysis. So we could not include all four of A, B, C, or D in the analysis, because we would create a scenario that's, the technical name for it is exact multicollinearity, but essentially we would over-constrain the system because we have all four of the possible options all included in there. We need to leave one of them out, essentially. So we could put in the bilevel variable for an A grade school, yes or no, B grade school, yes or no, a C grade school, yes or no, and we would have to leave out that last variable for D, or any one of the four. But let's say we left out the D grade school variable. Then any house that was zoned for a D grade school, it would simply have zeros for each of the other three variables, A, B, or C. So that way we capture all the information without including all the variables and over-constraining the system. And the way we would interpret that is that if, for example, the A grade school variable became significant, while the slope of that, the coefficient for that variable, would be the premium for being in an A grade school as opposed to a D grade school, or whichever was the one category that we left out. So just an interesting caveat when we're dealing with multi-level categoric variables. All right, one other thing I want to point out is that we have the possibility with linear regression to model non-linear variables based around this linear relationship with a variable. But suppose our variable was something that was inherently non-linear. Let me give you an example. Supposing, remember we saw a number of bedrooms ended up not being significant. Supposing we felt really strongly that there should be a relationship with number of bedrooms, and it occurred to us that maybe it's just not a linear relationship. Maybe the relationship is with the square of the number of bedrooms, perhaps, or something else that's non-linear. Well, how could we even test for this possibility using linear regression? The key is to create a new variable, and I'm just going to call it bedrooms squared. Okay? And this new variable is going to be a non-linear transform of the original variable. So I'm just going to take the original variable and I'm going to raise it to the power 2. And I'll copy this down so that in every case I have not just the number of bedrooms, but the square of the number of bedrooms. And if I were to run this as a potential explanatory variable in my linear regression, I would end up, if the coefficient was significant, with a term in there that had a slope multiplied by number of bedrooms squared. And it's a linear term in this new variable that I've modeled, number of bedrooms squared, but it turns out to be a quadratic coefficient, if you will, for number of bedrooms. So it's a way that we can actually use the math of linear regression to model a non-linear variable just by creating a transformed variable. So I could do this with the square of the number of bedrooms, the square root of the number of bedrooms, the natural log of the number of bedrooms, any nonlinear transform that I could do on any one of my numeric variables. And some of these are particularly useful, and the economists will use, for example, natural logs of certain variables a lot, especially if those variables tend to be heavily skewed to the right or something of that sort. But again, it's another option where we can extend the capabilities of our linear regression tool to capture these potential effects that may be significant for non-linear relationships. All right, so this covers our learning outcomes on regression analysis. It's based again on our scatter plots and our analysis of the relationship between variables. And what we've done is determine the least squared regression model, both for simple and multiple regression, and talked about the critical terms of the model. The coefficient of correlation, coefficient of determination, and the standard error of estimate, and other things. We've seen the ANOVA test and its usefulness. And lastly, we've been able to pull out the actual model equation based on the coefficients and determine whether or not those coefficients were significant. So that wraps up our discussion on regression analysis.